So we're looking at the non-spatial diagnostics in a least squares regression. And very quickly, I am going to import the needed modules. I'm going to import the files. Oops. This didn't work. There we go. So import the modules, input the files. The variable names, it's always the same setup that I use. And then we set up the read the shapefile and read the weights. We do the little trick for the kernel weights. If you don't read the kernel weights, but you make them straight within PySAL, either from a shapefile or from a data frame, you don't have this problem. It's only when you read them. And then finally, we set up the variables. We're going to run the regression with X2, which has the 3 explanatory variables. And so I'm going all the way down. We did all this last time. We saw the change in the estimates. We saw the predicted values, the residuals, diagnostic plots, and the map of the residuals as a standard deviational map. And finally, that you could get the table output of the coefficients as a LaTeX table. Okay. So as I mentioned, the default is that the non-spatial diagnostics are included. So if we run this regression, we get the full set of standard output. A lot of this is the same as before, but you see all these other things here. We have sum of squared residuals. We have 2 different estimates of the error variance. So the residual sum of squares divided by the degrees of freedom, which is the unbiased one, or divided by the number of observations, which is the consistent one. So all this stuff is down here with the R square and the adjusted R square. And then on this side, we have an F statistic, which is pretty useless in just about any regression. The test on the joint significance of this coefficients is always significant, and sometimes with very high significance. So this is basically 0. And then we also have, and this is useful later. So as I mentioned, one of the ways we're going to estimate a spatial lag model will be by means of maximum likelihood, where you maximize the log likelihood. Now, for a standard regression, if you assume normality, you can also compute the likelihood. And then you can compare the log likelihood for the standard regression to the log likelihood of the spatial regression. And the difference between these is called the likelihood ratio test, gives you a measure of whether it's worth doing the spatial model or not. We'll revisit that later, but that's why this is included. It's very easy to compute. And then these 2 are information criteria. These are in the same spirit of an adjusted R square. So an adjusted R square penalizes dr square for the number of variables that you include. As you include more variables, your R square will always go up, always. The question is, does it go up enough? Is it worth the cost of adding these additional variables? And so as your K, your number of variables, goes up, your adjustment to the R square is bigger. So you get penalized more. These information criteria are similar. As I mentioned the other day, the likelihood, or maybe I didn't, but the likelihood is kind of a pseudo goodness of fit. It's really actually a probability. So it's not a measure of fit per se, but it's used in its stead. And so in the same spirit, the likelihood gets better, larger, as you add more variables. Same way. So these two information criteria penalize for that. And they do it in two slightly different ways. I have it down there exactly how it does it, but essentially they take the likelihood and put in a penalty. And they're slightly different. For both of them, smaller is better. So for the likelihood, because you maximize the likelihood, larger is better. Right? For these information criteria, smaller is better. This Schwartz criterion is also sometimes called BIC. Especially in the Bayesian literature, you see this BIC or BIC is the same thing. So then those are kind of measures of fit. We have the same as before, that doesn't change. And then here we have some rough diagnostics that I talked about last week. Multicollinearity. This is the condition number. This is based on the eigenvalues of x prime x. Rule of thumb, over 30, you're having issues. Definitely if you have hundreds or thousands, you have a problem, right? Test for normality, Jacques-Barat test. 2 degrees of freedom. This is based on the asymmetry, the skewness, and the thick tails, the kurtosis, the fourth moment, okay? In many applications in practice, you will reject the null that the errors are normally distributed. Does this matter? Not as much as it used to, because we use larger and larger data sets. So then we get normality, not by assumption, but from the CLT, from the central limit theorems. So it's kind of a more modern take on things. You don't worry about normality as much as when you worked with 25 observations or 30 observations, right? Then heteroscedasticity, very important in a cross-sectional setting. Almost always will you reject a null. So not constant error variances. These two tests, one is based on the Lagrange multiplier principle. We'll talk about that later. The other one is a robust form, robust for asymmetry and lack of normality, basically. And they typically give you the same indication. So here's the expression for the Akaike information criterion. So minus twice the log likelihood, plus 2k. So the larger k, the more you penalize. And here's the same thing, but k times log of n. So a slightly different correction. Which one is better? Don't ask me, okay? They usually point in the same direction. You know. Okay, so those are the standard non-spatial diagnostics SPReg gives you. There's a couple of other ones available that are not default because they require more computation, especially if you have a lot of explanatory variables. This can add some time to the computation. This day and age, that's less and less an issue. Your machines are getting better and better. Remember, we wrote this thing 15 years ago, you know, first time, actually more like 20 years ago. So the machines were different. They were not nearly as fast. So you might as well include this if you can. Essentially, it's very similar in spirit to the Broich-Bacon test, but so the Broich-Bacon test is again an augmented regression type of thing, where you regress the squared residuals on the squares of the explanatory variables. And the test is basically a measure of fit. You know, there shouldn't be any systematic variability. Remember how we did the diagnostic plot of the regression residuals, and things should be kind of parallel. If you have fan shapes or some other irregular things, we have a problem. This is the same idea. You do an augmented regression, there shouldn't be any explanatory power If there is, you reject a null. The white test not only has the squares, but also has the cross products. So it's a little bit more powerful, but it usually gives you exact same result as before. So if you include this, you just get an extra line here at the bottom with the results of the white test for heteroscedasticity. And you see the number of the degrees of freedom are different. Here we have 3 explanatory variables. So we have 3. When we also include all the cross products, we end up with 9. Okay. Then the variance inflation factor, if you recall, is basically a test to see how good a fit the other variables provide for each individual X variable. So ideally, but this never happens unless you use principal components or something like that. Ideally, the X columns should be orthogonal to each other. They should be totally uncorrelated. In practice, they almost always are correlated to some extent. So if you regress each of the X's on all the other X's, you don't want that to be a good fit. So basically, you get the R square of that regression, you take the complement and you take the inverse of that complement. That is called the variance inflation factor. And you could just play with this and you say in your head, if I had an R square of 90%, 0.9, the variance inflation factor would be 10. You know, if
square or adjusted R square?
not adjusted, no, raw R square. Yeah. Because the reason it doesn't need to be adjusted, the K is always the same. So you always regress one of the variables on the remaining variables. So the K is always the same, no need to adjust. So here we go. If you do this, where am I? So again, everything is the same, except now at the bottom you have this nice little result. And just to check it, if you look, for example, at this one, this is the highest one, but it's not very high. This says, so the tolerance is 1 minus the R square of a regression of the Black variable on Hispanic and the economic deprivation index. So the R square should be 1 minus 0.23, right? So around 0.77. And we could check this in here. So we're regressing. Remember, I showed you how to do this, how you could set up alternative arguments in a regression specification. So this is the Y variable. It's part of X2. This may seem a little confusing, but this is Y. And then these are the other X's. So we just run this regression. And if you see right here, here's the R square, which is exactly 1 minus this value. So that's how it all hangs together. The higher the fit, the more of a problem you have. So we have, I think later on in one of my examples, we have a variance inflation factor of more than 100. Then you know you have a real problem, right? It means that the 99+% of the variance in that explanatory variable is explained by the other explanatory variables. So why include it? You don't need it. You already have all that explanation, right? Okay, so we did this. Then you can also do an F-test on the joint significance of coefficients. The way this is set up in spreg right now. So I mentioned the F-test as it is not very useful because it's always significant or just about always. So this is a way to run an F-test. The limitation is that it's on the joint significance of the last DF variables. And in a second, I'll show you slightly more complicated, but more general way of doing this. So if you want to check, is the last coefficient significant? You don't need to do this, but just to see how it works, we get exactly the same significance as that we had in the original regression. You know, we can show that if you take the square of this, then you get the exact same result as here with the same p-value. You can set them, you can use them set to 3 for all of them. You could set to 2 for, say, the last two variables, and that they're all, since they're all 3 highly significant, they're joint significance. You don't actually need to test this. I do want to spend 1 minute on the wall test. And this is for any general, this you have to think matrices again. Any constraint on the coefficients that can be expressed as a matrix, a set of equations, basically. So a set of linear relationships between the betas as set up in this R matrix. So for example, if you have 4 betas and you want to check whether the first and the third are jointly significant, or actually whether the first and the third are the same. So beta 1 equals beta 3. Then the beta vector is of 4 rows, 1 column, 1, 2, 3, 4, right? The R is just a row vector that says 1, 0, -1, 0, which translates into beta 1 minus beta 3 equals 0. Okay. If you have 2 constraints, you have 2 rows. If you have, 4 constraints, you have 4 rows. So you have this matrix of 1s and 0s, or whatever it is. If you want to check whether the third coefficient is twice the first coefficient, then it would be 1 minus 2, or 2 minus 1. Any combination that expresses your particular constraint that you're interested in. And then this is the result. The simplest case is 0, but it doesn't have to be 0. For example, if you have 2 elasticities in economics that have to add up to a particular value, that value would be in Q. Okay, let's say beta 1 plus beta 2 equals 2. Then in Q you would have 2, and you would have 1, 0, minus 1, 0, or plus 1, 0, and anything that you can express this way. Then this is a general result, is that asymptotically this monster is chi-square with as many degrees of freedom as you have constraints, J. Now, why is it not a monster? Again, let's do our matrix expressions. RB prime. So J by K by K by 1 is J by 1, flipped is 1 by J. This one is going to be J by J. This is going to be J by 1. So we end up with a scalar, single number. Okay. So this is very, very powerful. Anything that you can set up in this matrix R, and with whatever you're interested in on the Q part, you set up this matrix expression, chi-square with J degrees of freedom. So we can do this in general. For example, what am I interested in here? Okay, let's say I want to be joint significance of coefficient of black and economic pain, basically. So that's number 1 and number 3. The constant is the first one. So in Python, that is 0, 1, 2, 3. And then in row 0, and then row 1, we also set a coefficient. So we set up the R here. Oops. Where is OLS 2? I never ran OLS 2. This one? Yeah. Yeah, I could have also just changed it. So you see our matrix, 2 rows, 4 columns, and beta, beta 1, or if the constant is beta 0, beta 1 equals beta 3. Then our Q vector will be 0 and 0. And the wall test, we pass the betas, R, Q, and the variance matrix. And this says they're very highly jointly significant. So that's the wall test. And you can do any combination you want. Since we're out of time, I'm going to stop it here. I'm going to cover the robust variance matrices when I talk about the same thing with two-stage least squares. So it's the same.